All right, so good morning. Let us start our lecture today. Last time, we was trying to solve the following equation. So we have a heat equation. So heat equation. All right, so in the previous class, we were trying to solve this heat equation, right? So you have dt of u is uxx, dxx of u. So x is taken in the interval from 0 to 1. And t is taken from 0 to infinity. All right? We have the boundary condition. So when x is equal to 0, u of ux at 0x at 0t is 0. When x is equal to 1, u at 1t is equal to 0, and the initial condition at t is equal to 0 will be ux0 is equal to x. All right? All right, so let us continue. In the previous class, what we were trying to do is to solve a heat equation. dt of u is dxx of u, right? Here, because x is has a second derivative, you need two conditions. X is from 0 to 1, t is from 0 to infinity. All right? So the boundary condition for x will be ux at 0t is 0, and u of 1t is 0, and the initial condition will be x, right? So we have three steps. Step number 1, you're going to split utx to be tt times vx. All right, so this is separable. So when you do this, you're going to obtain a system of two equations, right? So you have Vn second plus lambda Vn is 0, and Vn at 0 is equal to Vn at 1 dx is 0. All right? So when you do this splitting, you're gonna have a system of two equations. The first equation is an equation of x only, right? So this is x, and this is x, and the first equation is an eigenvalue problem. All right? And the second equation is an equation of t only, plus lambda n t is equal to 0, right? Right? So the key idea of everything is to do the splitting here. Splitting or separating of variables. So this is an equation of x only, and this is an equation of t only, right? So the key idea in this techniques is that when you do the splitting, you suppose that utx is tt times vx. You're going to obtain an equation of x only. This is an equation of x, all right? And this is an equation of t, right? So step number 2. So step number 2 is to find Dn. right? So to solve the eigenvalue problem, Vn second plus lambda and Vn with boundary condition, dt of x Vn at 0 is equal to Vn of 1 at 0. Alright, so the second step, we will try to solve the eigenvalue problem. Alright, so when you solve the eigenvalue problem, you're going to find a basis. We find a basis Vn and eigen values lambda n in the x space. Alright? So in the second step, you're going to have to solve this eigenvalue problem to find a basis in x space. Right? It's clear? But we need two space, right? So we need x and t, right? So step number 3, solve the equation for t. All right. So when you solve the equation for t, the equation for t is very standard, right? So you have Tn prime plus lambda at Tn is 0, which means that Tn prime is minus lambda Tn, and this means that Tn prime over Tn is equal to minus lambda, and this means that log of Tn prime is minus lambda, so which means that log of Tn is minus lambda Tn plus C0. So Tn is C times e to minus power minus lambda t. So I can forget about the c, but I'm gonna come back to the c later, right? So in the previous class, we know how to solve the equation for t, right? So the equation for t has only one kind of solution, right? So the equation for t has only one solution, right? So I explain again. For the equation for t, this is a first order differential equation. Tn prime plus lambda n t is 0, right? So Tn prime is minus lambda n Tn. So you divide both sides. You have Tn prime over Tn is minus lambda, which means that log Tn prime is minus lambda n. And log Tn has to be minus lambda n t plus C0. So Tn has to be e to the power minus lambda n t. There's a constant here, but I just throw it away, right? So this is standard. The step 3 is always standard, right? So in all of the things, the difficult thing is to find this basis, but you know how to do it from the previous classes. But I'm gonna show you how to do it in this case. So step number 4, we have the basis. E to power minus lambda t times Vn, right? So you're gonna multiply e to power minus lambda n t with Vn, right? Times Vn. So the solution will be utx is the sum of Cn e to power minus lambda n t Vnx. So this is the basis in T and X space, right? So X. All right. So is this clear? So I explain again. So from step 1, what you do is you split U as the product of T and X. So T is a function of T and V is a function of X. Alright? You plug it back to the equation. Then you split the equation into two equations. One equation is for x only, and the other equation is for t only, right? So the equation for x is an eigenvalue problem, and the equation for t, so this is an eigenvalue problem, so the boundary condition will be the same here, right? So the ux at 0 is 0, will go to dx of Vn at 0 is 0, because here you remove the t, so there is no t, right? The second boundary condition will be similar with the second boundary condition of u. So what you do is you just remove t, right? So the boundary condition of the first equation of x only will be the same with the boundary condition here, except that here you have t, because you have two variables. In this case, because you remove the t, you have only one variable, right? And so this becomes the standard boundary condition that you have in the previous class. So the last one is Tn prime t plus lambda n Tn is 0. Of course, there's a boundary condition for this one, but I haven't touched because I'm going to sum everything here. Right? Now, for the first one, I'm going to solve this eigenvalue problem, and I'm going to find the basis Vn and a series of eigenvalues lambda n. Alright? Now this equation for x will be solved in a couple of minutes. So we go to the easy part. We're going to solve the equation first for t. Alright? So how do I solve the equation for t? This is first order. So Tn prime plus lambda n, Tn is 0. So the solution is always of this type. Tn is exponential minus lambda n t. Right? So now we have the basis for the t and x space. You multiply this guy with Vn, and you have a new basis. Alright? In the previous one, Vn is just the basis in the x space. Right? So here we are solving in two space. So you're going to have a basis for t and x space as well. So the solution will be the sum of Cn t to the power lambda n t Vn x. Right? So our task now is to find Cn. So you have to find Cn. So in order to find Cn, what you do is you replace t to be 0 here, right? So you have u of t x will be the sum when n is going from 1 to infinity of Cn e to power minus lambda n 0 Vn x. And because this is 1, so what I have is n minus 1, n is going from 1 to infinity of Cn Vn x. Alright? So now Cn will be the coefficient of u0x, which is x, in the new space. So this is x. So you have to find Cn. Alright? So Cn will be the coefficient of x in the expansion of x on the basis Vn. Right? So we're going to do that in a couple of minutes. So Cn will be the coefficient. So Cn is the coefficient of x expanding in the expansion on Vn of x. Alright? So far so good. So I explain again. So after you have this basis, right? You're going to expand utx is Cn times e to power minus lambda n t Vn x. Alright? So how do you find this Cn? You find this Cn by replace t to be 0. So when t is 0, you have x is u0x. Here you have e to power minus lambda n 0, which is 1. So you have x is Cn Vn. Alright? So then you have Cn Vn, and you take the sum, which means that Cn will be the coefficient of the initial condition x on Vn x. Right? Questions? So basically this is the scheme that we're going to have to use to solve the heat equation. in the heat equation, you have the first derivative in time and the second derivative in space. Right? Questions? It's clear? So I explain again one more time from the beginning. Right? So in this case, you have the heat equation. In the heat equation, you have the first derivative in time is equal to the second derivative in x. All right? So you have two boundary conditions. You have two boundary conditions for x. So the boundary condition for x will be at x is equal to 1 and x is equal to 0. And you have one initial condition when t is 0, right? So what you do is you suppose that u is the product of a function of t and a function of v, of x. So they are separate. So this is separating method or splitting method. So so when you do that, so in order to obtain this equation, what you do is you suppose that, all right. So I show you how to obtain this equation without doing the computation. All right. Right. So you have this equation. All right. Now you suppose that. That this equation is independent, u is independent of x, of t. All right, so then you're gonna have dxx of u is equal to something, and then you have u of x and is 0, and u of 1t, right, is 0. All right. So this is a trick. The trick how to you remember this formulation without doing the computation. All right. So you suppose that u is independent of t, right? So this dt will go away. So this guy will become the xx of u. All right. So this is an operator. You need to put something on the right hand side. So this is boundary condition. And x is equal to 0 and x is equal to 1. All right? So because this is independent of t, so dt of u is 0. So here you are supposed to have 0 here. All right? So here you don't have t. Right? All right? So then here you just replace by lambda u. All right, so this is something that you have to put by hand, but the other terms can be obtained by just removing t, right? So, for instance, for this equation, v second is coming from this dx of u, right? And then dx of v at 0 will be dx of u at 0 here, and this vn at 1 will be this guy here, right? So what you do is you just put the eigenvalue in there. But this is not. This is just a way how to remember the formula, right? Right. So when you do this splitting, you're gonna get one eigenvalue problem on x and one first order differential equation on t, right? So this eigenvalue will produce the eigenvalues lambda n and the eigenvector phi n. So the eigenvector phi n will be the basis in x space. All right. So this is solvable. I'm gonna solve it in a minute for you, but this is solvable. Now you have to solve the equation for t. The equation for t is also easy to solve. It has only one solution. Tn is exponential minus lambda n t. All right. So now you have the basis on t and x by multiplying this guy with the basis on x. So you have e to power minus lambda n t phi n. All right. So the solution will be utx, and you take the linear combination of e to power minus lambda n t times phi n x. All right. Now you have to find this Cn. So how do you find this Cn? You're going to use the initial condition. The initial condition that was written here. So the initial condition is x is u at 0t. So you replace t to be 0. So So e to power minus lambda t will be e to power minus lambda times 0. This is 1. So you have Cn Pn. Alright, so x will be Cn Pn. So Cn will be the expansion of x, the coefficient of the expansion of x on Pn. Right? Questions? It's clear? So this is going to be the exam. Right? So the exam will be the heat equation. So the final exam will be, because we have 3 hours, right? So there will be 2 questions on heat equation. So if you do heat equation, you cover everything like eigenvalues, eigenvalue problems and expansion and everything. So heat equation will be in the exam, the final exam, and you have 2 questions on heat equation. The optional questions will be the wave equation. So in the class, I'm gonna go over the wave equation, but I don't go into that in details because it's gonna be a little bit difficult. But I'm gonna spend 1 lecture on wave equation. It's gonna be the same. It's gonna be the same. But here you have second derivative, so you have to do more work because here the equation for t here is first order, but for the wave equation, this one will be second order. So because this one is second order, you're gonna have to do some more work, right? But I'm gonna spend only 1 lecture on that because this is difficult stuff. So I'm gonna put it into the optional questions, right? Questions? So we're gonna do practice exam next week. We're gonna do a lot of practice exam. So now let us try to solve. So now, after you understand the scheme, what I'm trying to do now is try to solve step number 2 and step number 4. All right? So step number 2. Step number 2. You have what? You have phi n second plus lambda n phi n is equal to 0, and then dx of phi, this is not dx, so this is phi prime at 0. So this equation is on 0 to 1, and then you have phi n at 1 is also 0. Right? Now, let us try to go to step number 2, in which we try to solve for the eigenvalues of this problem, all right? So you're going to find lambda n and phi n such that phi n second plus lambda n is 0 and x is in 0 to 1. So phi n prime is 0, it's phi n at 1, and they are both 0, right? So how do you resolve this problem? Characteristic equation. Right. Can you sign the back of that? So characteristic equation. So you have x squared plus lambda is 0. Alright? So now x squared plus lambda is 0, which means that we have 3 cases, right? And only 1 case gives you the eigenvalues and the eigenfunction. So case number 1, lambda is negative. Alright, so when lambda is negative, x squared will be minus lambda, and this is the absolute value of lambda. Alright? When lambda is negative, x squared will be minus lambda, and this is the absolute value of lambda, right? So which means that you have 2 roots. Root number 1 is square root of lambda, and root number 2 will be minus square root of lambda, right? So the solution will be C1 exponential of square root of lambda t plus C2 exponential of minus square root of lambda t, right? So I repeat. So we now we're gonna solve the eigenvalue problem in step number 2, right? In step 2, you're gonna solve this eigenvalue problem So this eigenvalue problem can be solved using the characteristic method, right? Questions? Yes?
Is it X or T?
X, thank you. Can you sign the paper, please? Right? So the first step is, the first case, lambda is negative, so x squared will be the absolute value of lambda. So the first root will be square root of lambda, the second root will be minus square root of lambda. The solution will be a linear combination of exponential of square root of lambda x and exponential of minus square root of lambda x, right? Now we're going to use this boundary condition. Boundary condition 1. So phi prime is 0, right? So phi prime at 0 is c1 square root of lambda exponential of e to the power square root of lambda times 0 minus square root of lambda c2 e to the power minus square root of lambda times 0. Alright? Boundary condition number 1, phi prime is 0 is 0. So phi prime will be lambda times c1 is exponential of square root of lambda c2. So I'm gonna write phi prime will be c1 square root of lambda e to the square root of lambda x minus c2 square root of lambda e to the power minus square root of lambda x. Right? So this is phi. When you take the derivative of phi, you're gonna have square root of lambda c1 e to the power square root of lambda, and here I have c2 minus square root of lambda e to the power square root of lambda x. Alright? I'm gonna plug 0 here and here. So I have c1 square root of lambda e to the square root of lambda 0 minus square root of lambda c2 e to power minus square root of lambda 0. So this is 1 and this is 1. So I'm gonna get square root of lambda c1 minus square root of lambda c2 is 0. This means that c1 is equal to c2. Alright? So I have c1 is equal to c2, which means that phi x will be c1 e to square root lambda x minus c1 e to square root lambda x. Alright? So I explain again. The first boundary condition can be solved by taking the derivative of phi. So, and you replace 0 into the first derivative. You obtain c1 is equal to c2, right? Now, because c1 is equal to c2, phi x will be c1 exponential of the square root of lambda times x minus c1 exponential minus square root of exponential of lambda x, right? So now we're gonna use the second boundary condition. Boundary condition number 2. Phi of 1 is 0. So phi of 1 is 0, meaning that 0 is c1 exponential of square root of lambda minus c1 exponential of square root of lambda. Right? Minus. Right, thank you.
It's a plus, right? The original phi of x?
Yes. Thank you. Thank you. Can you sign at the back of the paper, please? So here you have a plus, right? And then you will have c1 e to the square root of lambda plus e minus square root of lambda, right? So c1 will be 0. C2 will be 0. So then you have a trivial solution. Alright? So I explain again. Using the first boundary condition, you find that C1 is equal to C2, right? Because C1 is equal to C2, phi will be C1 exponential of the square root of lambda times x plus C1 exponential of minus square root of lambda times x, right? Now you're going to use the second boundary condition. The second boundary condition is that phi1 is 0. So because phi1 is 0, you replace 1 into this formula. When you replace 1 to this formula, you have 0 is C1 exponential of square root of lambda plus C1 exponential of minus square root of lambda. You put C1 as a common factor, right? This is a positive term, which means, so because this is equal to 0, you obtain that C1 is 0. Because C1 is 0, C2 is also 0, and you have a trivial solution. So there is no eigenvectors in this case. Case number 2. Lambda is 0. So the equation will be phi n is 0. So phi will be a x plus b, right? The second case is the easiest case because lambda is 0. When lambda is 0, phi second will be 0. Phi second is 0 means that phi is ax plus b, right? So so now you use the boundary condition number 1. Phi prime at 0 is 0. This implies that a is 0, right? So phi will be b, which is a constant. Boundary condition number 2, phi of 1 is 0, which also means that b is 0. So this is also again give you a trivial solution. Alright? So I explain again the second case. The second case is lambda is 0. So when lambda is 0, you replace 0 here, you get phi second is 0. So when phi second is 0, phi is ax plus b. You use the first boundary condition, phi prime at 0 is 0. Phi prime at 0 is a, so a is 0. So phi is a constant b. You replace the second boundary condition, phi1 is 0, into the equation, you find b is 0. So in the second case, you also have a trivial solution. So there is no eigenvalue and eigenfunction. All right. The last case, case number 3. Lambda is positive. All right. So lambda is positive means that x squared plus 0 is equal to 0 has 2 roots. The first one is I square root lambda, and the second one is minus I square root lambda. All right. The last case is lambda is positive. So when lambda is positive, you have two solutions, I square root lambda and minus I square root lambda. Right? So and this is, in this case you have C1 sinus of square root lambda x plus C2 cosinus of square root lambda x. All right? I explain again. So in the last case, lambda is positive, so x squared plus lambda is 0, has 2 roots. The first one is I square root lambda, and the second one is I minus I square root lambda. So the solution will be C1 cosinus square root lambda sinus of square root of lambda plus C2 cosinus of square root of lambda, right? So now you want to use the boundary condition. So I compute the derivative. So phi prime will be C1 square root of lambda cosinus of square root of lambda x. Alright, so minus C2 square root of lambda sinus of square root of lambda x. Alright? I'm going to take the derivative of this guy. So sinus derivative will be cosinus. And remember the square root of lambda here. Cosinus derivative will be sinus with the square root of lambda here. Minus square root of lambda. Right? So now I'm going to use the first boundary condition. Boundary condition 1. Phi prime at 0 is 0. So phi prime at 0 is 0, which means that 0 is C1 square root of lambda cosinus of square root of lambda times 0 minus C2 square root of lambda sinus of 0 square root of lambda times 0. Alright? So this gives you 0. This gives you 1. Right? So which means that 0 is C1 square root of lambda. So C1 is 0. Right? So I explain again. Here you have two roots, I square root of lambda and minus I square root of lambda. So you have two solutions, cosinus square root of lambda and sinus square root of lambda. Now you're gonna take the linear combination of them. You replace the first boundary condition, phi prime at 0 is 0. So this is the derivative of solution. You replace 0 here. So I have C1 square root of lambda cosinus square root of lambda times 0. I replace 0 here. I have C2 square root of lambda sinus square root of lambda times 0. So this sinus of 0 gives you 0. And this sinus of 0 gives you 1. So you have 0 is C1 times square root of lambda, which means that C1 is 0. Right? So in this case, because C1 is 0, you have phi x is C2 cosinus of square root of lambda. Right? Because C1 is 0 already, I replace it into the form of phi. So the left over is cosinus of square root of lambda. Right? Boundary condition number 2. Phi 1 is 0. So because phi 1 is 0, cosinus of square root of lambda C2 is 0. Right? Right? So C2 cosinus square root of lambda is 0, means that square root of lambda is n plus 1/2 pi. Right? So the eigenvalue will be n plus 1/2 square pi square, and then the eigenfunction will be cosinus of n plus 1/2 pi x. All right. Right. So I explain again. I put minus is better. This is it. This is minus. All right. So I explain again. So after you replace phi prime as 0 is 0, you get C1 is 0. So now phi will be cosinus of square root of lambda x, right? Now you're going to use the second boundary condition. Phi 1 is 0. So phi 1 is 0 means that cosinus of square root of lambda is 0. So cosinus of square root of lambda is 0 means that square root of lambda is n minus 1/2 pi. So lambda n will be n minus 1/2 pi square. And the eigenfunction will be cosinus of n minus 1/2 pi x. Right? Questions? Now you have the eigenvalues and the eigenfunction. Right? So the solution So after this, after the step of finding eigenvalues and eigenfunctions, you know that the eigenvalues will be n minus 1/2 square pi square, and eigenfunctions will be cosinus of n minus 1/2 pi x. All right. So the solution will be, now we go to step number 4. So utx will be the sum when n is going from 1 to infinity of Cn e to power minus lambda nt phi nx. Alright? This is a general formula for the solution. Right? Now I'm gonna replace lambda n, and I get this is the sum when n is going from 1 to infinity of Cn e to the power minus n minus 1/2 pi square cosinus of n minus 1/2 pi x. Alright? It's good. So we know from the previous, in the first part of the lecture, we know that e to power minus lambda nt times phi will be something like a basis for t and x. Right? So you multiply them and you need a constant c. Constant c will be computed later. Now you have lambda n, which is over there, and phi n, which is over there. I'm going to replace lambda n by n minus 1/2 square pi square, and phi n by cosinus of n minus 1/2 pi x. Right? Questions? Yes?
Would there still be a t in that, the e to the power
Thank you.
negative?
Thank you. Yes. Can you say at the back of the paper, please? There's a t there as well. All right? So now we're going to compute Cn. Compute Cn. So you have u 0x is equal to, I'm going to replace t to be 0 there. And I'm going to have Cn e to power minus n minus 1/2 square pi square times 0 cosinus of n minus 1/2 pi x. Right? So this, I know that this is x. So I replace 0 into t, and I get this is sum when n is going from 1 to infinity of Cn cosinus of n minus 1/2 pi x. Alright? It's clear? So I explain again. So in this formula, this is the general formula for the solution. So this is Cn e to the power minus lambda nt phi n. So this is e to the power minus n minus 1/2 square pi square t cosinus of n minus 1/2 pi x. Right? Now I'm gonna use the initial condition, right? The initial condition is x, so I have x is u0x. I replace 0 here, but this guy, when it is 0, the whole thing will be 1. So this will be x is Cn cosinus n minus 1/2 pi x. Alright? So how do I compute Cn? Cn will be the coefficient of x in the expansion on the basis. So what is the formula for Cn?
The inner product of f and phi n over phi n phi n.
Excellent. Can you sign the back of the paper, please? Yes. This is a very excellent answer. So Cn will be inner product of x phi n dividing by phi n. Phi n, right? It's clear? So here, I'm gonna have the integral from 0 to 1 of x cosinus of n minus 1/2 pi x dx dividing by the integral from 0 to 1 cosinus square of n minus 1/2 pi x dx. Alright? So Cn is a coefficient, right? So the formula that you have to use is you multiply x with phi n in the inner product and you divide by phi n phi n. So the inner product of x and phi n is this integral, and the inner product of phi n is this integral, right? This is excellent answer. Now let us compute the first guy. So this guy will be cosinus of n minus 1/2 x dx. Right? So this is something that we do all the time. What should we do?
Integration by parts.
Excellent. Can you sign the back of the paper again, please? So now we are gonna do integration by part again. So we have d. So this is d of sinus of n minus 1/2 pi x dividing by n minus 1/2 pi, right? So now you have to do integration by part. You observe that cosinus is sinus prime dividing by this factor, right? So this is 1 over n minus 1/2 pi integral from 0 to 1 of x d of sinus of n minus 1/2 pi x. Alright? So this constant does nothing, so I put it outside. So this is the guy that I have to do. So now I'm gonna do integration by part, and I have 1 over n minus 1/2 pi. I have x sinus of n minus 1/2 pi x from 0 to 1 minus integral from 0 to 1 of sinus of n minus 1/2 pi x dx. Alright? So the first step, you observe that cosinus is the derivative of this guy. So I'm going to have x d of this guy, right? So this is a constant. So I put it outside. I have x d of this guy. So this is a db. The integration by part gives you ab minus b di. Alright? So that gives me minus 1/2 pi sinus of n minus 1/2 pi x 0 to 1. This guy, the antiderivative will be cosinus of n minus 1/2 pi x dividing by n minus 1/2 pi. You take the difference from 0 to 1. Alright? And you get what is the coefficient? This is sinus of n minus 1/2 pi dividing by n minus 1/2 pi minus 1 over n minus 1/2 pi squared. Alright? And forgot the n minus 1/2 outside. This is outside. Right? So it's clear. So at the last step, what we do is that we plug the initial condition here. Cn will be the coefficient of x in this guy, right? So in order to compute this, you're gonna use this formula. Right? So in order to use this formula, you have to do the first integration dividing by the second integration. The first integration can be computed by integration by part, and this gives you this one. So in the next class, we're gonna compute the second integration. Questions? It's clear. So have a nice weekend.